Suppose we have m linear equations in n variables, which takes the following form. We define something called the coefficient matrix, which is a table consisting of all the coefficients aij's, which is enclosed by a pair of brackets. Each horizontal line of numbers is called a row, and each vertical line of numbers is called a column. So there are m rows and n columns in this coefficient matrix. We also define what is called the augmented matrix, and it is the coefficient matrix with an extra column which consists of the numbers on the right-hand side of the system. For easy reading, we put a vertical line to separate the coefficient matrix and the last column. For now, we just need to know that a matrix is a table of numbers enclosed by a pair of brackets. We will talk about matrices on their own in full detail later. Let's look at a simple example to get used to reading systems in the form of augmented matrices. For this particular augmented matrix, we observe that the last row means that 0 times x1 plus 0 times x2 plus 0 times x3 equals 2. In other words, 0 equals 2, and it is clearly a contradiction. So this means that the system has no solution, and so it is inconsistent. Now, we want to talk about how we can solve systems in general. Let's first look at a 2x2 example. That is, two equations with two unknowns. We consider the system 5x plus y equals 17 and 3x minus 2y equals 5. The augmented matrix looks like this. We know all about how to solve these kinds of systems, and one way to start is to observe that the coefficient of y in the second equation is 2 times that of the first equation. So we can eliminate y from the second equation by adding 2 times the first equation to the second equation. For the augmented matrix, this means that we add 2 times the first row to the second row. We get 13x equals 39, and the first equation is kept unchanged. Now, we wish to divide the second equation by 13 to get the value of x. So that means we will multiply the second row of the augmented matrix by 1 over 13. We get x equals 3, and the first equation is still unchanged. Then, what we might use to do is to substitute the value of x into the first equation to get the value of y. But here we will do something similar to the first step, which is to add some multiple of one row to the other in order to eliminate one of the unknowns. Here, we will subtract 5 times the second row from the first row to eliminate x. We get y equals 2. We have already found the solution, but if we want to write things more nicely, we can swap the first row and the second row to get x equals 3 and y equals 2. What we have done in the example in solving this system are the following 3 things, where we denote the ith row of the augmented matrix by Ri. The first one is that we swap 2 rows, and even though this was the last thing that I did in the example, I put it as the first point since it is sort of the simplest. In symbols, this means that Ri and Rj are interchanged. In other words, the ith row and the jth row are swapped. The second thing that we did was to multiply a row by a non-zero number, say lambda. In symbols, this means that Ri it becomes lambda times Ri, and this means that I have multiplied the ith row by lambda. The third thing that we did was to add a multiple of one row to another row, and in the symbols, this means that Ri is changed to Ri plus lambda times Rj. This means that I have added lambda times the jth row to the ith row. These 3 things are called elementary row operations. So now the question is, how do we apply elementary row operations to solve a system systematically? Let's consider the following system as an example, with 3 equations and 3 unknowns. Let's write it in the form of an augmented matrix. The first step that we want to do is to eliminate x1 from the second row and the third row. To do so, we replace the second row by the second row minus 4 times the first row, and replace the third row by the third row minus 3 times the first row. We get the following augmented matrix. Observe that the first number in the second and the third rows are both 0. In other words, x1 is eliminated from these two rows. The second step is to change the coefficient of x2 in the second row to 1, and we can do so by multiplying the second row by negative 1/3. We get the following augmented matrix, and indeed, the second number in the second row becomes 1. The third step is to eliminate x2 from the third row, and we can do so by replacing the third row by the third row plus 5 times the second row. We get the following augmented matrix. Observe that the second number in the third row becomes 0, so x2 is eliminated. The fourth step is to change the coefficient of x3 in the third row to 1, and we can do so by multiplying the third row by negative 1. We get the following augmented matrix. Now, the third row means that x3 equals 3. Note that we have written the augmented matrix in such a form, such that the second row only contains x2 and x3, and the first row contained all three variables. So, we can substitute the value of x3 into the second row to get the value of x2, and then substitute the values of x2 and x3 to the first row to get the value of x1, hence solving the system. So we first substitute the value of x3 into the second row to get x2 plus 2 times 3 equals 4, which means that x2 equals negative 2. Then, from the first row we have x1 plus 2 times negative 2 plus 3 times 3 equals 9. So x1 equals 4. That means that we have found the solution to the system where x1, x2, and x3 are 4, negative 2, and 3 respectively. Note that this method of finding the value of one variable from one equation and then substituting it to the equation above it to find the value of another variable and substitute again to the equation above it and eventually finding all variables is called backward substitution. And we can do so because we have written the augmented matrix in such a nice form using elementary row operations. We will talk about matrices of this form in the next video.